Here are parts C and D, problem 53, chapter 8 of McMurry's 6th edition organic chemistry textbook. Again, the problem says, how could you use Diels-Alder reactions to prepare the following products? Show the starting diene and dienophile in each case. And so, again, what I've mentioned before is that in a Diels-Alder reaction occurs between a diene and a dienophile to give you a cyclohexene. So you want to try to identify a six-membered ring with a double bond in it, and then push the arrows backwards. Start the foot of your arrow on an alkene, and just start going around, taking every other carbon and just moving it around in that same direction. Okay, you want to come back into the starting. Okay, so don't wander off in different parts of the ring. Stay within that six-membered ring with the double bond. And what we get here when you draw this out is a double bond here. The arrow's pointing to a single bond, so that changes it to a double bond. And you form a double bond down here as well. The arrow's pointing to a single bond. Remember, if the foot is coming off of a double bond, it changes to a single bond. So you form this molecule, or thinking in the forwards direction, butadiene would be a reactant. And what's left over is we put a double bond here, and we draw the rest of the molecule. Now, the thing that is not clearly understood by the explained by the textbook, or probably your instructors in class and so on, is how you would think beyond this. I mean, this looks like a great answer, but if you look over here, this is a cyclohexene as well, and that's a cyclohexene as well. For reasons that I won't get into, we don't want to mess around with the middle ring, but let's take a look at this ring on the right. It looks like that itself could be formed from a Diels-Alder reaction also. So let's go ahead and take this double bond here and start moving the foot of our arrow on the double bond, okay, and proceed in the same direction all the way through that six-membered ring. And what you get is this symmetrical dienophile and another molecule of butadiene. Okay. So when I was a student, I was kind of annoyed. Well, how are we supposed to know that? Well, you just have to keep filling with it and then kind of self-discover it, or perhaps do a lot more reading and studying. So the final answer here is that we would take the dienophile here shown on the left and actually two equivalents, I'll put a 2 in front of this, two equivalents of butadiene. The first would add maybe to the right, and then the second would add to the left, and you would get this product over here. Okay? There's a lot more detail here, like, for example, why are these hydrogens going back and these ones going forward? But again, I won't get into the details here. All right, so let's take a look at this molecule here. We could break this down in one of two ways. We could say, well, this is the double bond I want to fiddle with here, and we could try to push it around. And in so doing, we would get the typical butadiene. And over here on the right, we would get a carbon-carbon triple bond with our ester. Okay? Well, okay, but what about the other double bond? If we draw the starting material out again, and I weren't knowledgeable enough about, well, which one how could it be made? Let's say I fiddled with this alkene and I said, well, I think this is my alkene here. So let's go ahead and push these around. Okay. And another possibility could be butadiene again. Oh wait, I'm sorry, I messed that up. It would be a carbon-carbon triple bond over here, right? The arrow's pointing to this double bond, so it changes it to a triple bond. and then we would have a double bond here on the lower right, and a double bond here on the upper right. Okay. So this is a very common situation in organic chemistry where you might break it down into two possible molecules, and then you have to analyze which of these would give a better yield, or which of these would be more successful or probable. The answer is this top reaction here, and the reason why is because electron withdrawing groups on the dienophile are more reactive for a Diels-Alder reaction. Okay, so you want electron withdrawing groups. Okay, EWG stands for electron withdrawing groups on the dienophile. Okay, not on the diene. So this would not be a good pairing for a rapid or successful Diels-Alder reaction. Okay, so you need to remember details as well. What makes a Diels-Alder reaction fast? Thanks for watching.